on you. Nice. Cool. Yeah, we'll look at DALL-E 2. It just came out 10 minutes ago. This is by OpenAI. If you want to investigate yourself, this is just the OpenAI blog. I have not seen this yet. So legit, this is the first time I'm seeing it as well. If you see something cool, let me know in the chat. Also, I have no clue. New camera. Very wide angle. Makes my arms really long. See? Really long arms. Excellent. All right. I mean, we'll just dive in, right? So we'll read this together. As I said, I have like this is the first time I'm seeing this as well. So, yeah. New AI system that can create realistic images and art from a description in natural language. That sounds interesting. So, and this is typical OpenAI blog, right? Where they just have their examples. Like, there's no way you're gonna interact with this, I guess. There's also a paper. So, they don't even put this on archive, right? Like, their papers, they're just on their own website. They're so famous. Hierarchical text conditional image generation with clip latents. So I think, let's search diffusion models. So yeah. So this is now no longer based. I think this is now based on diffusion models, which was to be expected. Sorry, Estras, this is not live coding. We'll just look at this new research that just came out, and we'll react to it in the moment. So, an astronaut riding a horse in a photorealistic style. Okay, so this it can create original realistic images and art from a text description. Can combine concepts, attributes, styles. So this is what we're used to, I guess, from the image generation models, but this obviously, so DALL-E was always, it's different than the clip notebooks and so on, the AI art that you're used to, because those are all mainly clip based, and then you put some kind of a model in front of clip and you optimize the whole thing. But DALL-E is a forward, so you input the text and then there's a forward propagation, and then the result is an image, and that's may or may not be filtered. So teddy bears shopping for groceries as a one-line draw. This is insane. So this is what this model can do, and there is a bunch of different images right here. Now these are, well, if they're not cherry-picked, at least they're curated, right? So they want to see that nothing bad happens when you look at these things. A bowl of soup that looks like a monster. What is this? Please, please, come on. Okay, this is insane. Really insane. Knitted out of wool, made out of spray painted on a wall. Wow. I mean, yeah, it depends how cherry-picked these things are, but this is really impressive. Now, I don't know if you've seen, but there is kind of a new Lion plus Clip notebook or something. Lion Clip diffusion. Let's just search for that, because this is also very, like, there's a new notebook, and I've seen this around Twitter. Yeah, exactly. There's this new notebook. This is not by OpenAI. This is in Clip that has been trained on this open source data set. And when people combine this with these kind of old methods of Clip notebooks, then this is what happens. So this is like weird, and it's funny because it can spell, but it kind of it is like, it is not, it doesn't spell really well. But if you, so there is this this research here, and these are already quite insane in quality, right? Latent and diffusion. I love generative models. That's actually good. A painting of a squirrel eating a burger. But now we're at this DALL-E, so these seem to be very much better. Now this model is based on diffusion, which means that it has some interesting capabilities. If you know diffusion models, technically what they do is they are creating their own data set in the sense that a diffusion model essentially iteratively refines a piece of input in multiple steps until it reaches the output. So it's not necessarily one forward propagation, although it depends a little bit on how you model it. You can have one layer for each of the denoising steps, or you can have the same neural network and you pass the input over and over again, maybe with some indication of what time step it is. So what a diffusion model does is it takes an image and it just adds noise to it step by step. So it adds a bit of noise, then it takes that, it adds a bit of noise, it takes that, until it is completely garbage, like until it is complete noisy. And at that point, you can reasonably assume by some limit theorem that this is now perfectly modeled by Gaussian noise or whatever noise you use. And because of that, because you have a process that results in a defined distribution, you can sort of make reverse inferences mathematically, which leads to some training properties that you can then use to train these diffusion models. In practice, what that means is that you take an image, you make it continuously more noisy, that's your training set. And what you train is the reverse. So you train always to go from one step in this denoising process to go to the little bit less noisy version of that image. So that's what you train. So this direction is easy, right? To make it more noisy. But then you train a neural network to make it always one step less noisy. And that essentially means that you can now sample the original thing, which you know is a Gaussian, so you can sample from that, and then you can send it through all of these stages of denoising, and at the end you'll end up with a really nice picture. And you can do that conditionally on text, which is what they do here. Now, given that this is what they do, they have some interesting capabilities. Notably, they can edit images. So they can start with an image and then edit that image. And they can even edit only parts of that because they can mask some of the parts and then simply apply the denoising diffusion process to that. So that's what they do right here. Now, I am going to, if you don't mind, just quickly put on Twitter that I'm live streaming right here, and maybe also on Discord. I hope this opens over here. Yes. 1 second. Nope. Yep. All right. Just writing the announcement, adding the little picture, and off we go. All right, yeah, so they can edit. So now let's see. Make realistic edits to existing images from a natural language caption. And this, I think, is what really will make a difference in sort of AI art. What they say, we use diffusion models for the decoder and experiment with both autoregressive and diffusion models for the prior. Is my mic muted? Is my mic muted? No, I think I just made the Twitter announcement and then I was quiet for 10 seconds. Sorry. All right, let's see. So you can make edits. So what they do is, here's the original image, and they select a location where they want to edit. As I said, you can edit images and you can do so in a constrained way. And one is, so you can select the location and you can prompt it to add a flamingo, right? That's the natural language prompt, is to add a flamingo. And you select the location where you want to add a flamingo. Look at these, this is insane. Look at these results. Add a flamingo to this. Okay. It's interesting that the flamingo style, right, matches the rest of the picture. It's not just a flamingo. When it's inside, it's this sort of, what is this even? Like, is this a piece of furniture or so? Like, this isn't, or a sort of a swimming device flamingo. Yet when you select it on the water as well, but when you select it outside, it's actually a real flamingo. So this is quite insane. It doesn't just add a flamingo, it actually takes the entire picture into account. Let's say add a corgi. Again, so this is the original image on the left, and then you select the location, and the prompt is to add a corgi. Now, notice that the style of the corgi changes depending on where it is, right? The left is this like the self-portrait of, is this the self-portrait of Van Gogh? I'm not sure, but and if you add the corgi here, it's actually a real corgi, right? So it's super powerful because it looks beyond, like it swimming device flamingo. I'm sorry, I don't know what it's called. So yeah, you can see this is all a real corgi. Whereas if you point into the image, it actually matches the style of the image drawn. So this is super, like, this demonstrates quite a bit of understanding, I believe, at least like integration of the entire thing. This is going to be a paid service, isn't it? Look, I don't know, because the interesting thing is they didn't even make DALL-E into a paid service until now. And because they withheld DALL-E, we got all of this, VQGAN plus clip and diffusion models plus clip things, which is like, I don't think that would have happened if they were just to release DALL-E even as a paid service. Let's see what else they have here. So we add a sofa. Yeah, so I think this is going to be quite huge for making any sort of visuals. Like, if I need to make thumbnails for these videos and all, so if you do anything like this is essentially, it is let's say a weak form of Photoshop, but that's automatic. So if you could give this to someone on Fiverr, and that's about what it would turn out, right? You could give the picture on the left and be like, I'd like to add a sofa in the back corner there, please do it. And that'll cost you, I don't know, $20, $50 or so on Fiverr. And this just works. So yeah, I'm excited to see what they do with it, because they do have like investors and so on can take an image and create different variations of it inspired by the original. Yeah, so this is essentially different variations. I don't know what they prompted with here. They don't say, as far as I can tell, but maybe maybe what they do is they sort of back propagate it, or they noise it a bit, and then they denoise again from the intermediate stage. So with these diffusion models, right, you can make an image more noisy, maybe change it a little bit in some intermediate layer, and then use the diffusion models again to upscale it. And maybe that's how they do these types of things. I'm not sure. They don't say right here. Maybe they say in the paper. This is, though, fairly interesting. You can see that there's two people on the left. Is this Klimt? I'm not sure. I'm not an artist person thing. Image to text embedding to image. That could be. But you can see that it is like the variations are really keeping sort of the semantic content here. And I believe that's also one of the powerful things of that's one of the powerful things of training image and text together, because text, by nature of being made for humans to communicate with each other, text is much more on the level of sort of the, what should I say this, type of information and the gradation of information that is important to humans. So training image and text together, I believe just by the nature of having the text in there, will give representations that are much closer to what humans would consider different or irrelevant or something like this. Like, this is, I mean, this, come on, this is insane. Look at that. Look at that. Wow. I think it's taking the generated embedding and then regenerating the image from that embed. Yeah, yes, exactly. So oh, you believe, okay, maybe they run it through the encoder, they don't actually noise it. That's very possible, yeah. Would this be possible with audio? I guess, yeah, you'd have to find a relevant noising process. I'm not sure if Gaussian noise or so is really appropriate for audio, but since audio is a continuous signal, I don't see why this wouldn't be possible with audio, especially if you train it with associated with text, right? I mean, yeah, this is crazy. It would be really interesting to see if sort of the representations of this stuff aligns with the representations of like real pictures of birds, or if they are way different. Because you can see here these style variations, they all depict the same subject and they are kind of in the same style, right? It'd be interesting to see how much it can actually differentiate that from it. It's also interesting that here they have these colored boxes in there. So do you think these might be the, is this an artifact of what? Is this like an artifact of the generation process? Like, is this they sample auto-regressively? Are they always the same? Yellow, light blue, green, red, blue. Yellow, light green, green, red, blue. Can't tell what they are. Look at that. I mean, yeah, this is like just the level of abstraction, and I'm not sure what people like Gary Marcus make of this. This would be super interesting to hear, because I mean, look at that. So it is clearly not a natural picture, right? It's not, yet it depicts a girl with headphones on the laptop, like apparently in some sort of garden or surrounded with plants, overlooking a city in the night sky with the moon, and there's a cat in it. And all of that is in all of these pictures. However, it's just different, right? It's a bit, look at, like, you can't tell me that this thing doesn't do some degree of abstraction, or it just brute forces all of this by training data, but I can hardly imagine. So, you know, 1 second. Has learned the relationship between images and the text used to describe them. It's used a process called diffusion, which starts with a pattern of random dots, gradually alters the pattern towards an image when it recognizes specific aspects. So yeah, for people who tuned in late, diffusion models, they create training data by making pictures more and more noisy. So they learn to reverse that noise. Let's see. Well, can you hear? You probably can't hear that sound, right? So, yeah, no? No? Okay. Let me quickly try. How about this?
Bot painted like a Picasso?
Now I can't hear it. All right, 1 second. Yep, this one.
Didn't think so. DALL-E 2 is a new AI system from OpenAI that can take simple text descriptions like a koala dunking a basketball and turn them into photorealistic images that have never existed before. DALL-E 2 can also realistically edit and retouch photos. Based on a simple natural language description, it can fill in or replace part of an image with AI-generated imagery that blends seamlessly with the original. It's called inpainting. In January 2021, OpenAI introduced DALL-E, a system that could generate images from text, like this avocado armchair. DALL-E 2 takes the technology even further with higher resolution, greater comprehension, and new capabilities.
Here's a video idea. I built a real-life avocado armchair. Let's do that. That's a future video. Promise. I should promise things like this. Okay. Promise.
Like inpainting. It can even start with an image as an input and create variations with different angles and styles. DALL-E was created by training a neural network on images and their text descriptions. Through deep learning, it not only understands individual objects, like koala bears and motorcycles, but learns from relationships between objects. And when you ask DALL-E for an image of a koala bear riding a motorcycle, it knows how to create that or anything else with a relationship to another object or action. The DALL-E research has three main outcomes. First, it can help people express themselves visually in ways they may not have been able to before. Second, an AI-generated image can tell us a lot about whether the system understands us or is just repeating what it's been taught. Third, DALL-E helps humans understand how AI systems see and understand our world. This is a critical part of developing AI that's useful and safe. The technology is constantly evolving,
just look like an
DALL-E 2
made
has
from
limitations.
actual avocados.
If it's taught with images that are incorrectly labeled, like a plane labeled car, and a user tries to generate a car, DALL-E may create a plane. It's like talking to a person who learned the wrong word for something. DALL-E can also be limited by gaps in its training. If you type baboon and DALL-E has learned what
we're
a baboon
at the
is through
broader
images and
impact
accurate
section.
labels, it will generate a lot of great baboons. But if you type howler monkey and it hasn't learned what a howler monkey is, DALL-E will give you its best idea of what it thinks it could be, like a howling monkey. What's exciting about the approach used to train DALL-E is that it can take what it learned from a variety of other labeled images and then apply it to a new image. Given a picture of a monkey, DALL-E can infer what it would look like doing something it's never done before, like paying its taxes while wearing a funny hat. DALL-E is an example of how imaginative humans and clever systems can work together to make new things, amplifying our creative potential.
There's a lot of hedging here, OpenAI. A lot of hedging against against people criticizing you. That's good strategy. You just hedge ahead of time. You're just like, hey, you can't do this, you can't do that. Howler monkeys are a species of monkey that indeed howls a lot. Well, then it's correct, right? DALL-E 2 generates more realistic and accurate images with 4x greater resolution. Okay, a painting in the style of Claude Monet of a fox sitting in a field at sunrise. Well, that is indeed a great picture. Yeah, do you think these things down here are the sort of initial tokens for some autoregressive prior? I'm not sure. Okay. Which we currently do not make available in our API. As part of our effort to develop and deploy AI responsibly, we're studying DALL-E's limitations and capabilities with a select group of users. Oh, let me be the select group of users. Oh no, I'd be terrible. I would be immediately cancelled. They're making it harder to share without knowing where it's from. Well, you can just cut off the bottom. Like that's safety mitigations we have developed include preventing harmful generations. We've limited the ability to generate violent, hate, or adult images by removing the most explicit content from the training data. Okay. We also used advanced techniques to prevent individuals facing those of public figures. Yeah, so you can do some things, right? You can do this at training data time, which is where you just say, I'll never expose my model to bad things, and then it doesn't learn bad things, which I don't think it can work, but not particularly well, because you're always going to miss some of that stuff, like a lot. Like you're going to miss most of that stuff, honestly. And therefore, so either you limit your training data to such a degree, or you're going to miss most of the stuff, because the number of ways that humans can come up with to do shady and things and harmful things, whatever that means, it's absolutely insane. So I trust humans to always generate things that you will miss, and you can do it at training time. So you can, if you have some sort of a classifier that detects harmful content or whatnot, you can discourage the generation, like at training time, of these things. And then at inference time, you can obviously also filter simply. If it generates something like this, you can filter that out. All of these things I find suboptimal, but I do understand that if you want to release a product like that, you don't want to necessarily have it output. It's already a stretch, right, for a company to provide a service where they themselves don't exactly know what it outputs, which is crazy with these new APIs. So I understand, but again, they told us GPT-2 was too dangerous to release. You remember that? When they told us GPT-2 was too dangerous? Yeah, so curbing misuse. Our content policy does not allow users... Okay, we won't generate images if our filters identify text prompts and image uploads that violate our policies. Yeah, okay, that makes sense. You just tell people, like, don't do it. Phase development, phase deployment. Okay, previewing, limited number of trusted users. Well, I hope they release it at some point, not like DALL-E 1. Right? There's a system card. We don't care about system cards. Okay, that's the blog post. So for people who've joined later, it's pretty insane what you can do. So this is a text to image system. An astronaut playing basketball with cats in space in a minimalist style. Insane. Yeah. And what it can do also is edit, which is going to be huge, right? Huge for anyone. Like if this is in some sort of Photoshop or GIMP or something like this, new world opens for anyone who has to make stuff. Like a lot, I don't think people realize, how much you could do if you have a presentation, and instead of having some stupid stock images, you just kind of generate something, and then after generation you edit it, right? The cool thing here is that you don't have to restart and figure out the prompt exactly. You can just generate something and then edit at some point. You can say, add this here, remove this, change it to this, and so on. And that's just, and make some variations, right? You can just say make some variations. And that, I believe, is going to be quite huge for a lot of people to just use casually, if that's how they intend to release it. And I'm very be very cool to see if there is an open source replication of that. Given how far we've come with Clip and with these new data sets, again, for people who haven't been here, there is this Lion 500M data set, and people have been training a Clip models on that. Oh no, so Lion 400M dataset. This is the old one. There's a new 5 billion one. And if you combine that with diffusion models, you can get pretty insane things as well. And then if you combine that with upsampling models, then you already have very powerful models. However, I don't know how fast they are. So the stock images of today might be the basis of all pictures in the future. Yes, pretty much. I think, you know, we are probably the generation who still makes real images and uploads them somewhere. And before that, it was just not possible because the internet didn't really exist in the capacity to support that. And after that, most images will just be AI generated. So, yeah, so that's, we're a special generation, the last real picture generation. Okay, let's just skim through the paper a bit and figure out how they, you know, a bit more about what they do. So here, Super Saiyan sentient bag of chips, ArtStation. It's, you know, they're using the, okay, controversial opinion, you know, given that they are using essentially discoveries of the open source Twitter community that was explicitly a reaction to them not releasing DALL-E 1, do you think it's appropriate that they are now using the tricks that community has figured out to make cooler images in their, again, proprietary system that they don't release and probably end up selling to you? Like, arguments for and against, right? But point of contention. Like, you, in my opinion, you know, go do all the selling you want, but then, you know, this is kind of, the ArtStation at the end is a bit of a, that's kind of a thing of the kind of sharing open source community. And yeah, not sure. Teddy bear on a skateboard in Times Square. This reminds me of that movie, Ted, no? A dolphin in an astronaut suit on Saturn. This is 1024 by 1024. So these actually become usable, let's say, in presentations and whatnot. The 256 by 256 was pushing it a bit in terms of resolution, but this actually becomes variations by encoding with clip and then decoding with the diffusion model. Okay. So this is, again, this is combined. Is this essentially clip-based diffusion? Okay, here it is. High level of unclip. This is, okay, unclip might be the variation thing, right? That's my prompt. Really? Avant-garde. So is this the whole method, or is this just where you make variations of a thing? Variations between two images, interpolating their clip image embedding and then decoding with a diffusion model. We fixed the decoder seed. Okay. So clip seems to play an actual role right here, right? So they have clip here with the clip objective, right? There's a text encoder and an image encoder, which they can give in. So this will give them some sort of an embedding. And then that embedding goes, there's a prior, and then there is this diffusion decoder. The dotted line, we depict our text to image generation process. A clip text embedding is first fed into an autoregressive or diffusion prior to produce an image embedding. Clip text embedding is fed through an autoregressive or diffusion prior to produce an image embedding. And then this embedding is used to condition a diffusion decoder, which produces the final image. Note that the clip model is frozen during training of the prior and the decoder. So there seems to be three components, right? The first component is clip itself. That's above the dotted line here. Hello, Philip Wong. Good to see you here. So, and they already either have clip or they train clip anew, but they first train clip, which gives them these embeddings of text and image, right, that correspond well to each other, and then they freeze that. And then there's two more parts to it, which are this prior thing, and the prior thing maps a text encoding to an image encoding. Right? So the clip objective simply makes them align, makes these encodings align. However, the prior actually transforms one into the other. It's interesting that they need that, and that you can't just have the have the text encoding be the start of the diffusion process, but apparently they put this prior here, and maybe that models that for a given piece of text there can actually be a lot of different images that go along with it. But since the two are probably already quite aligned, it might require some minor modifications to it. And then there's the diffusion decoder, right, which we saw. You can train all of this probably from the same data sets. So the clip you can train, obviously. Then once you have clip, you can train the prior to simply translate the text embedding that you get from the frozen clip encoder to the image embedding that you can get from the frozen clip encoder. I'm not sure if that what happens, but yeah. And then you can train the decoder likewise, simply by encoding with clip and then trying to reverse that process. Although again, I don't know if that's actually what they do. So let's read into it. Again, this is I'm seeing this for the first time as well, so I'm as clueless as you are. Does anybody have a link to the paper? You got to go to openai.com, click on DALL-E, and then click on View Research. A training data set consists of pairs of images and their corresponding captions. Given an image X, let ZI and ZT be its clip, image, and text embeddings. We design our generative stack to produce images from captions. So it's image from caption, not the other way around. Using two components. A prior that produces clip image embeddings conditioned on caption. So yes, so these here are clip image embeddings. They're not newly trained ones. So the prior translates the text encoding to the image encoding. Again, which is special because the clip objective already aligns them during training. So that, again, that might require some minor modifications to them. It's interesting that they have to have it. And a decoder that takes in text captions, again, conditionally, and the clip embeddings, and produces image condition on clip. So this is not the same, if I have this correctly, as like clip-guided diffusion. Because in clip-guided diffusion, we take a diffusion model and we feed that into clip, right? We take a diffusion model and we feed that into clip. And then we try to backpropagate the clip loss to the diffusion model and try to guide the diffusion model in this way. Here, it's different. Here, we actually use the diffusion model, but we don't start from noise. We actually start from an embedding. That's very interesting. And I'm going to guess the prior translates to the clip embedding, and then we start from that. That's very interesting. So the decoder, yada, 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 yada. Okay, projecting and adding clip embeddings to the existing time step embedding. So this is a variation of the glide model. By projecting clip embeddings into 4 into 4 extra tokens of context that are concatenated to the sequence outputs from the text encoder. We retained the text conditioning pathway, yada yada. But find that it offers little help. We enable classifier-free guidance, which is also nice, by randomly setting clip embeddings to 0, 10% of the time, and randomly dropping text caption 50% of the time. So this is a conglomerate of sort of the recent advances by OpenAI and by the community. It goes back from the decoder back into clip. It kind of sounds like they just modified the clip embeddings and output via the image encoder. Zoom, bap, boop. Yes, exactly. They modify the clip embeddings via the prior first and then via the diffusion model. Okay, the prior. To generate high resolution images, we train 2 diffusion upsamplers, one to upsample images from this to that, and another one to further upsample them. To improve robustness, we slightly corrupt the conditioning images during training using Gaussian blur. Okay. Is this, I guess, so it'd be interesting to know if this is end-to-end, these upsampling methods, because to really get good generations right, the upsamplers would need to also be informed of the prompts and so on. Otherwise, the details are kind of generic, and the big structure is, which is usually what you want, but it's not exactly what you want. Prior, while the decoder can invert clip image embeddings to produce images, we need a prior model that produces ZI from the captions to enable image generations from text captions. So there is an autoregressive prior. The clip image embedding is converted into a sequence of discrete codes and predicted autoregressively, or a diffusion prior. The continuous vector ZI is directly modeled using a Gaussian diffusion model conditioned on the caption. Okay. That's cool, I guess. For the diffusion prior, we train a decoder-only transformer with a causal attention mask. An embedding for noise. Sorry, my reading style is not conducive to live streaming. I guess I'll adjust. So here is how they train the loss. So the image embedding is fed into this one, along with the time step and the text description. The F, I'm going to guess, is a noising process or something like this. And then this is the target. So this is now a, let's say, true diffusion model, where we continuously noise what we want to achieve, and then we try to reverse that. Variations. We are given an image, we can obtain its clip image embedding and then use our decoder to invert, producing a new image. To make the variations more similar, we first perform this inversion with the decoder conditioned on ZI. Okay, so it seems like clip has a big part in this, which is a bit surprising, but not too much. Because the original DALL-E just used clip as a sort of ranker at the end. Whereas this one uses clip intrinsically in the process. So It uses, if it gets a piece of text, it puts it through the clip text encoder, which is frozen, right? And then it has the prior and the diffusion. Exploring the clip latent space using the unclip decoder. Okay, this is again the variations. Variations of images featuring typographics attack. Predicted probabilities across 3 labels. Surprisingly, the decoder still recovers Granny Smith apples, even when the predicted probability of this label is near 0%. So what they do, they project these images into the clip latent space and then decode them again. Can it generate text? It cannot. I mean, it can probably generate text as part of an image, as you can see right here. So this is an apple. And even though the classifier is, what kind of classifier is this? Okay, this is clip. So here you feed this image into clip. This was, I think, a famous experiment. You feed this image into clip and you ask clip which of the text classes is the most likely. And clip says the iPod class is very likely. And when you actually project that and then upsample it again, you can see that it's interesting because clip sees mostly an iPod, right? That's the class is 99.98% versus Granny Smith's 0.02%. Now this is normalized, which is why I think that this still works. So they say the surprising part right here is that it in fact retains kind of the apple. It retains the Granny Smith apple, even though technically clip mostly sees the iPod. But I think that's kind of, because it probably still sees the apple, but when you let it classify, it's just that much closer, to the iPod text label rather than to the apple. But it probably, the visual information in here, like the encoding of that, is still very much contains the apple motive. But I guess this is what they wanna demonstrate. It's so funny how it can. This is the same thing, right? It's the same thing as this thing right here, in that it's kind of bad at spelling. Like it's so interesting that it can in fact write text, even though it's an image producing model. It can write text in pixels, but it's really bad at spelling. Like, yeah, why? Nobody knows. Okay, let's spend a whole bunch of time on this prior right here. Clip image embeddings, reconstruct them with progressively more PCA dimensions. Okay, so we take the image on the right, I'm gonna guess, and we project it into the clip latent space. And then we only retain the top principal axes, or the top principal components, and then we recreate them again. So there is, you can investigate a little bit what is kind of important. So it seems, let me try to make this a bit bigger. It seems like you can see the detail gets added as you go up. So this here is kind of a scene from food. Here you have a city that's might even be, I don't know what city that is. I'm sorry. And the bottom one, a bunch of cows. This could be Switzerland. Oh, we know. So yeah, as you would expect, it first tries to model kind of the general framework, general setting. It seems to match the colors even a little bit. It's like the colors, general setting, what is it? So And that's really interesting, right? That means the sort of highest level information that it has really refers to kind of concepts. It does refer to color, which and things like this, but also to concepts, right? So there's no view of a cow here on the left, or the specific city in the middle right here. It's just like a city landscape, which is really interesting, because a lot of models, I think they would much more try to model everything at once, but in less detail, right? And then if you go down with the principal components, they would try to just have color blobs everywhere where they're relevant. And you can see as you go up, as you add principal components, what's also interesting is that as you add principal components, the scene can radically change, right? So that's also quite interesting. So here we can, on the top row, you can see that we now add tomatoes into the mix. So where it went from a general, are these gnocchi maybe? So from a general Italian kitchen setting, it goes more and more into this direction, and it ends up in something that's fairly similar to what we're seeing, right? And the same here on the bottom with the cows even. You can even see that a little bit they have even the same positioning, but I'm not sure if I'm over-interpreting this right here. You can also see that you have the general mountain landscape down here, and then more and more it kind of refines to the maybe a bit more correct colors. A bit also the background gets a bit more accurate. Yeah, it's just quite cool. And as I said, this is just a lot of evidence for the fact that these things have some sort of abstractive representations of what's happening. Samples using different conditioning signals for the same decoder. We passed it in the first row, we passed the text caption to the decoder and passed a zero vector for the clip embedding. In the second row, we passed both the text caption and the clip text embedding of the caption. In the third row, we passed the text and the clip image embedding created by an autoregressive prior for the given caption. Note that this decoder is only trained to do the text to image generation task without the clip image representation. So they have a lot of inputs, it seems, into their decoder. So what is the first one? We pass the text caption to the decoder. So there's no text embedding from the clip decoder or anything. There's only the text caption, which it also conditions on. A group, an oil painting of a corgi wearing a party hat, hedgehog using a calculator, motorcycle parked in a parking space next to another. Yeah, so this, as you can see, the top row, it picks up kind of on like one word or so out of the, is this intelligent? Is it like we should make the meme with the butterfly? But as you can see, it kind of picks up on like one word or so out of the text, and then it just creates kind of a realistic image that contains that word. It doesn't have the capability of fusing different things and so on. And I'm not sure what that is, because they say it's the same encoder and that has been trained with various inputs, and they just pass a zero vector for the clip embedding. So they kind of stifle the input. It's not a true comparison in the sense that they have actually trained the decoder to only work with this type of data. So I'm not sure what this means right here. It could mean that clip embeddings are really important. It could also just mean that you have to actually train the decoder with this, because you just stifle it from some inputs that it doesn't have. Now, if you add the text embedding from clip, you can see that it already gets a lot more capable. So a hedgehog using a calculator. Yeah, there is a hedgehog and there is someone, I guess, using a calculator. Motorcycle, or this wire metal rack holds several pairs of shoes and sandals. I guess, not really. And then as soon as you add the image embedding as well, so that's the image embedding of created by an autoregressive prior for the given caption. Okay, so the prior will create the image embedding. So this is the full system at the bottom, except having a clip image embedding that comes from some sort of image instead of from the prior. Yeah, it's difficult to say what this means, honestly, because they just take away stuff, and obviously it's not gonna go as well. So the classifier-free guidance is, I don't actually have it in my head exactly what it is, but it's like maybe you have a classifier. I don't know what they use as a classifier here. Maybe clip itself. And then you can mask some stuff, and then you have the direction of where you want to go. And then you just go more into that direction, but I don't have it on top of my head what it is. Okay. Glide. I've done a video on glide, so I don't remember myself too accurately what it does, but I love how the different papers continue this work, right? So DALL-E, glide, make a scene, and then unclip a green train coming down the tracks. Crazy. Yeah, this goes into the direction of GANs, which just have become so good at this point that the optimizations are micro. We're still a few ways away from there, but it's getting there. Samples from unclip and glide for the prompt. A red cube on top of a blue cube. Yeah, pretty good. Reconstructions from the decoder for difficult binding problems. We find that the reconstructions mix up objects and attributes. In the first two examples, the model mixes up the color of two objects. In the rightmost example, the model does not reliably reconstruct the relative size of the two objects. Yeah, so probably, given this might also be a property, right, of the text descriptions. Maybe not the binding problem as much, but the relative sizes, you rarely have a text description that describes the relative sizes of things, and therefore the encodings might just end up with sort of what's contained in the image. And then that's what the models learn, that, okay, what's mostly important is what's contained. A sign that says deep learning. Deep. This is just deep. Come on. A high quality photo of a dog playing in a green field next to a lake. Unclipped samples showing low levels of detail for some complex scenes. Okay. Yeah, so DALL-E 2, DALL-E 2 and unclip seem to be the same model, right? So that just because I was wondering, sort of because they kept talking about unclip, but I do believe that DALL-E 2 is unclip. Oh, correct me if I'm wrong right here. But here they describe it. Yes, this is unclip. That's DALL-E 2. This thing right here. So yeah, I don't know what to think of this. It's certainly super impressive what it can do, right? If you look at, ooh, there's join waitlist. Okay, we'll do that. It's certainly super impressive. Like, the applications of this are, I believe, quite far-reaching, because this allows more and more. Yeah, it decouples, I think, the mechanical. I've already said this, I think, in the past. It decouples the mechanical skill of making these things happen, like the Photoshop skill or the painting skill or nunchuck skills, fighting skills. It decouples the mechanical skills from, or it decouples them from the creativity part. So usually you have like, okay, I want to do something, and then the second thing is, okay, I have to actually implement it. And this thing decouples it. It kind of takes that mechanical aspect away from you, and therefore you're left to focus on what should happen. And I think with these editing capabilities that it can do and the variation capabilities, this could be very powerful if built into GIMP. And then in GIMP you can just say, okay, enter text, a piece of text, create an image, okay, edit here, enter a piece of text, make some variations on this thing right here, select a bunch of stuff. Very, very powerful. And I guess a lot of people would pay a lot of money for it, which might be the end goal here. All right, I hope you enjoyed this kind of live reaction to this type of research. I'm excited to see if this actually ever gets out here. But yeah, let me know how you like this type of stuff if we do live reactions in the future again. And yeah, I guess I'll see you around. Thank you very much for being here. I'll stop the stream now. Bye-bye.